All right, so today we are going to learn about the second
Fundamental Theorem of Calculus.
There's just something about the way that sounds that just makes me feel like it should be said like that. The second fundamental theorem of calculus is basically something that you have already seen with the first fundamental theorem of calculus. It's just a slight little change to it. Remember that we have already been looking at how we can do the derivative of things when the letters, we'll say, or the variables aren't using x, and that it's not in respect to x. In fact, as we move forward in these units ahead, we're going to be dealing more with word problems. And let's be honest, things aren't written with x. They're written in terms of time, or in terms of weight, or in terms of you fill in the blank. So looking at this in the respect of t seems to make more sense. Now, what's more is I want you to see the notation that's being written here. The integral of a function of t, dt, with respect to t, okay, would be then written as capital F. That's the notation that is used. Capital F basically saying we took that integral. It went up, right? It kind of went up to a capital. It went up a power, or however you want to think of integrals. And so that capital F is the notation that's used when you take the integral. And it would be evaluated from x to a. So then you would plug in the x and you'd plug in the a. The important thing to note, though, sometimes you'll see questions where this isn't left as x, but actually is a function. And so that in and of itself will pose another issue. And so we want to look at that a little bit more as we move ahead. So, all right, and maybe even see what kind of patterns we'll notice as we do this. So let's just do this question here. The integral of 3t squared would be t cubed, right? And we would evaluate from x to 2. And so then we would plug that in, right? We plug that in for the t. And so that would become x cubed minus 2 cubed, or 8. Does that make sense? So we simply just plugged in that x. Does that make sense? Now let's look at this. If we have the derivative of that integral, what would happen? If I did the derivative of this, what would I get? The derivative, so now changing gears, should change colors here. So now let's take this and let's do the derivative of this. And the derivative of that would be 3x squared, and that minus 8 would go to 0. Well, what do you notice about these two things? If I take the derivative of the integral, many of you would automatically just say, oh, they cancel out. But remember, this is in terms of t. And we have x here, and so is this an x. So the important thing to see here is that when you do the derivative, that this x actually does play a role. So the derivative of the integral, evaluated from x to a, what does that mean? That means we're doing the derivative, so that would be the integral of f of x minus the integral of f of a, would equal simply the derivative of that integral, which would just be the function in terms of x. Much easier fix than that, isn't it? And so here in this yellow box, basically what the second fundamental theorem of calculus is taking that fundamental theorem of calculus of that integral and just extending it to what happens when you do the derivative of that integral. And of course, it ends up proving our point that it, in essence, cancels each other out, but it replaces that t with the x. So let's look at some examples as to how to apply that. So rather than having to do the integral and then doing the derivative, the truth is, once we recognize that second fundamental theorem of calculus, we can say, oh, well, the derivative of the integral is basically that same function, 3t squared, but in place of it, we would put 3x squared. And that would be the answer to that. The derivative, how about this, of the integral of sine t, dt, would simply be sine of x. Now, once again, if you don't believe what I'm saying here, let's just try that out. So that would mean we would do the integral of sine, which would give me negative cosine, right, of t, evaluated from x to pi. And so then that would be the negative cosine of x minus the negative, so that would make that positive cosine of pi. And of course, the cosine of pi is -1. And so now let's do the derivative of that. And so to do the derivative of this, right? The derivative of negative cosine would become sine x minus 0. And so the answer, of course, is, right? We could have done that pretty quick, right? Why are we wasting our time? Well, that's kind of the point. Let's start with this next question. This one says f of 0. Notice it's the capital F. And so what it's telling us here is it wants us to put 0 in for x, right? And so this is really a fancy way of saying going from -5 to 0 of this integral. All right, so what we have to do here is we got to do the integral of this. Does that make sense? Or rather, the area. The easiest way to solve this is rather than putting the powers in there and going up a power and all that good stuff, actually instead, a better way, and probably the actual way you should do it, is think about what that graph is. That's a half a circle, right? It's the top half of the circle. What's the radius? Good. And so this is saying from -5 to 0, so it really only wants a quarter of that circle. So that would make it, the area would be pi r squared, or 25 pi, divided by 4 for a quarter of a circle. Well, this says f of 5, which would mean instead that you're doing the integral from -5 to 5. So instead of being a quarter of the circle, it's only half a circle. So hopefully I can quickly answer that for you with 25 pi over 2. All right, well, now it wants the slope at 3. And so it helps to recognize that fundamental theorem that we just talked about, the second fundamental theorem of calculus. The derivative of the integral from -5 to x of this, as we just learned, is actually simply the function there, but in terms of x. And so when it says f prime of 3, all that really means is we're doing the square root of 25 minus 3 squared, or 9. And so that would be the square root of 16, or 4. How about double prime? Well, that means that if this is f prime of x, then f double prime, what would we do there? You would do its derivative, right? So let's just think about that. That would mean you would have to do 25 minus x squared to the 1/2 power. And so that would become 1/2 25 minus x squared to the -1/2 times the derivative of the inside. And so then again at 4, right? Just to simplify this out again, the 2's divide out. I would have -x over the square root of 25 minus x squared. So now when I plug in that 4, we would have -4. And we'd have the square root of 25 minus 16, which of course is 9. Square root is 3, so that makes that -4/3. And that's just proving that second fundamental theorem of calculus, how it can be useful for us. And the fact that you're doing the derivative of an integral, that does in fact cancel it out, so to speak, and replaces it with just f of x.